Okay, so hello everyone, and welcome to the question regarding the open die forging. So remember that the forging in general is going to be a process that's similar to the combustion test, and that's how we're going to explain the methodology for this process. So the question that we have is about a cylindrical workpiece, which is going to be subjected to a cold offset forging operation. The starting piece is going to be 75 millimeter in height and 50 millimeter in diameter. It's reduced in an operation to a height of the 36 millimeters. The work materials has a flow curve that defined by the K value of 350 megapascal, and the N exponent is equal to 0.17. Assume that the coefficient of friction in this scenario is equal to 0.1. Determine the force and the process as the process going to begins, and the intermediate heights of 62 millimeters, 49 millimeters, and at the height of the 36 millimeters. We have to remember something here, that in the case of the forging, we are going to reduce the size, the height, but the volume will remain the same. Okay, so if the height is going to be changed, okay, the volume remain the same. That's mean that the diameter is going to be increasing. That's hint number one. The hint number two is that if I'm going to change the height, of course the strain will be increased, and thus the part is going to get harder as we're going downward, because we're going to have the phenomena of the strain hardening. So before I get start to do the calculation, we need to have an introduction about the analysis of the open die forging with no friction. If we have no friction occurs between the work and the die surfaces at the contact points here, then the homogeneous deformation will occur. You can see that the height just changing, so that the radial flow and uniform throughout the work part height, and the true strain can be given by the equation of that the strain is equal to the initial height divided by the final height. The flow stress is going to be equal to the K value multiplied by the strain up to power n. So the HO is starting height, and the H is the height of at some point during the compression. H can be the final height. The HF through strain reach the maximum value. Oh, I should have something here. Now, in real life, we're going to have an open die, usually going to have a friction to be combined with. So the friction between the work and the die surface constrain the lateral flow of the work, and this results in the barreling effect, because these two surfaces are going to be attached. But still, we need to reduce the height. So what's happening is that this now not moving due to the friction, and thus we are going to have the barreling effect for the part. In a hot open die forging, the effect is going to be even more pronounced due to the heat transfer at the die surface, and this will cool the metals and increase its resistance to deformation. However, the forging force is going to be calculated by multiplying the Kf by the Yf by the A. The A, of course, is going to be the area, the Yf is the flow stress, and the Kf is the forging shape factor, and that's something related to the friction. So you can see that the equation to calculate the shape factor is going to be 1 plus 0.4 multiplied by the coefficient of friction multiplied by the diameter, which is going to be the instantaneous diameter, divided by the height, which is going to be the instantaneous height. Okay, so I'm going to use this equation to do the calculations for the force required for the forging operation. So we go back to our example. Once again, we are going to highlight the parameters given to us. First, I know the K, I know the N, I know the mu, I know the initial height, the HO, I know the DO, the initial diameter, and I know the final diameter in this state, but we have been given another two heights need to be considered, which is the 62 and the 49. But at the beginning, we would like to know what will be the force just when we start adding the force of the forging. So the solution is going to be start with the following. First, as the process just begun, the workpiece volume, which is going to be constant all the way, is going to be equal to 75 pi multiplied by the diameter square divided by 4. Okay, so 75 is the height, pi multiplied by the radius diameter square divided by 4 is going to be the area of the base, and this will give me that the volume is 147,262 cubic millimeters. So the moment contact is just made by the upper die, the height is going to remain 75 millimeters and the force is going to be equal to 0. But at the start of the yielding, the edge is going to be slightly less than 75 millimeters. And we can assume that the strain is going to be 0.002. Then the flow stress now can be calculated. Remember that this value is just an assumption. We just started the compression test for the part, and we consider that strain is going to be at this value. So the flow stress now is going to be equal to the K that's given to us multiplied by the 0.002 up to power n. And this gives me that the flow stress is equal to 121.7 megapascal. Next step is I can calculate the area, which we have the same area. We didn't change anything yet at the 75 millimeters. So we're going to have the area is equal to diameter squared divided by 4 multiplied by the pi, and this will be 1963.5 millimeters square. Calculate shear factor. Okay, we have 1 plus the 0.4 multiplied by the mu by this, multiplied by diameter divided by the height. And we are going to have that the shear factor is equal 1.027. Now we have everything to apply the equation for the force. Okay, so the force is going to be equal to the Kf multiplied by the Yf multiplied by the A. And the force now is equal to 245,410 Newton. Now the height is dropping, so we can calculate the strain. We said that the true strain is equal to the initial height, which is 75, divided by the instantaneous height, which is here 62 millimeters. We'll get that the strain has been increased from 2 in 1,000 to 0.1904. We recalculate the value for the flow stress. We're going to have 264 megapascal. Now, we know that we are going to have a constant volume. So the new area is going to be the initial volume, which is remain the same, divided by the new height. So we can get the area now equal to 2,375.2 millimeters squares. Now I can find the new diameter, I can find the new Kf, and I can find the new force. So the new diameter now has been increased from 50 to 55. Now the Kf is going to be calculated according to new diameter, and new height is going to be 1.035. Then I can calculate the value for the force. So you can see that by changing the height down to 13 millimeters, the force has been almost multiplied by 2.5. Okay, so that's due to the strain hardening. If we are going to repeat the calculation once again for the two heights of the 49 millimeters and the 36 millimeters, we'll find that the force at 49 is going to be 955,642 Newton. At 36 is going to be 1,467, 1,467,422 Newton. And if we're going to sketch that, this will be the height against the forging force required to do the work. Okay, so That's what we have for the case of the forging, and we're going to move